Right, so let's look at an example where we want to determine the rate law of a given reaction, and we're going to do that using the method of initial rates. And basically what that means is we mix a bunch of reactants, we know the initial concentrations, and we measure the initial rate of that reaction and use those rates to then determine what the dependence of the reaction is on the concentrations of the reactants, which is then by definition the rate law. So let's start by thinking of what is a rate law and rate constants and so forth and so forth. Right, so we can read the question says, use the following data to determine the overall reaction order and the value of the rate constant K. And then in B, it asks us to determine the rate of the reaction when a given concentration of NO and H2 is reacted. So the basic point where we want to start is what is the rate law of a reaction? That is something where if we write the rate of a reaction, so rate is equal to some constant, which is the rate constant, multiplied by the concentration of the reactants, or the first reactant, so NO, raised to some power, not the stoichiometric coefficient, some power, multiplied by the other reactant, so H2, raised to another power. Once again, not its stoichiometric coefficient. And what we want to investigate, we want to determine this K, and we want to determine this M and this N. Now, M and N can, of course, have values of 0, 1, 2, can also have -1, but in a rare case, it will have an inverse value. And how we do that is we, of course, keep one of them constant. So let's say, for example, we keep H2 constant. So we keep the concentration of H2 constant, and we test in two different experiments. We have a concentration of H2 of 1 molar, and we have a concentration of NO of 1 molar. And then in the next experiment, we again have a concentration of H2 of 1 molar, but we double the concentration of NO to 2 molar. And we see what happens to the rate. Does the rate double? Does the rate triple? And hence, by doing that, we then can identify what does this M imply. Is this M a square? Because if the rate doubles, it means that rate must be some form of proportional. So in other words, if there's a doubling, it just means if we double the concentration, the rate. If the rate doubles with doubling the concentration, it means there's a 1-to-1 ratio between the two. So it means the rate in terms of that reactant is 1-to-1. If the rate, for example, what the word I'm looking for? So if you double the concentration, but the rate quadruples, then you know it's second order in terms of that reaction. So in other words, squared. So it's NO squared, and the rate quadruples, and so forth. So that's essentially what we're doing here. And then you swap it around. You keep the other one constant, and you vary the other one, and you see how the rate responds to varying those concentrations. So that's the method of initial rates in principle. But how does that look in terms of the mathematics? So what we do here, so let me write that again here at the bottom. So we say, in general, the rate of this reaction is going to be equal to K multiplied by NO raised to the power M multiplied by H2 raised to the power N. Okay. Our first starting point, so to determine, M. Right. That's where we start. To determine M, we need an experiment where we vary the concentration of nitrous oxide, so NO, but we keep H2 constant. So let's look at the table for something like that. So where does NO's concentration vary, but H2's concentration remains constant. Now, the only two experiments where H2's concentration remains constant is experiment 1 and 2, and of course NO's varies. So there's a difference there. So we can use experiment 1 and 2. So let's write that down. We say, therefore, compare experiment 1 and 2. And how we do that is we say the ratio between the experiment 1 and 2 needs to be the same as the ratio between, well, the rates of those experiments. So this means the rate of experiment 1 divided by the rate of experiment 2 is going to give us some ratio, right? But what is the rate? It's that expression there at the top. So the rate is this K, and it's the concentration of NO. But what concentration of NO? It's the concentration of NO in experiment 1 for the rate in experiment 1 raised to the power m. And here it's the concentration of H2 in experiment 1 raised to the power n, divided by the rate in experiment 2 is K, the concentration of NO in experiment 2 raised to the power m, multiplied by the concentration of H2 in experiment 2 raised to the power n. All right, and now you can actually substitute the values if you would like, and you should see something important. But we can do some things with our logic. Our first thing is the whole idea of a rate constant is that it is a constant. So that should cancel. That is something that will cancel immediately. So we can just go ahead and cancel that. The reason we chose experiments 1 and 2 is because the concentration of H2 is the same in those two experiments. So that should cancel. Even though we raise it to n, it's the same value to the power n. Even though whatever n is, we don't care. N will be the same value in both cases. So we can just cancel that. So that leaves us with a situation where we say the rate of experiment 1 divided by the rate of experiment 2 is going to be equal to the concentration of NO, experiment 1, divided by the concentration of NO in experiment 2 to the power m. And of course, if you have something to the power something of this to the power m divided by something to the power n, you can write it as both things to the power n. So you can write here NO experiment 1 divided by concentration of NO experiment 2 to the power m. All right, and now we substitute in values. So the rates are for experiment 1, the initial rate is 1.3 times 10 to the minus 5, so it's 1.3 times 10 to the negative 5. And you can write molar per second, but it's divided by the same thing. So I'm not going to write the units, but okay, maybe we write the units because that's what we need to do, molar per second. And the experiment 2, I quickly check that as well. Oops, that's really terribly written. It is 5.2 times 10 to the power minus 5 molar per second. It's equal to the concentration of NO in experiment 1 is 5 times 10 to the negative 3, 5.00 times 10 to the negative 3 molar, divided by experiment 2 is 1 times 10 to the negative 2, 1.00 times 10 to the negative 2 molar, all raised to the power m. So if you quickly do that, you should get it works out quite nicely. It's going to give you a quarter. It's equal to a half to the power m. How nice, eh? Okay, and how do we solve this? Well, we need to take the log on both sides, or ln, same thing. So you take log of a quarter equals to log of a half, half to the power m, and half to the power m is the same as m log a half. In other words, we just solve for m, so of course we're going to divide everything by log a half, and hence m is equal to log of a quarter divided by log of a half, which you will get a 2. So this means, therefore, the reaction is second order in terms of NO, right? Because it's NO to the power 2. So this means if we double the concentration of NO, it should quadruple the rate. If we triple the concentration of NO, it should sextuple the rate. Yeah, I think that's the word. So you understand. So that's what it means to be second order in terms of a reactant. It's not second order overall reaction. Remember, that is when we sum all the powers of all the reactants, but it's NO squared, means for that one reactant, it is going to be squared. Right. So that is what this means. But it's just for that one reactant. The overall reaction order is something else, but just some interesting point. Okay. But that's not all. So we have M now. The next thing we need to do is we need N. And hence we need to find something where NO remains constant, or the concentration of NO remains constant, but the concentration of H2 varies. So let me do that in another color. Which color? Maybe purple. Yeah. Okay then. So to determine N, let's look for one where the concentration of NO remains the same, but H2 varies. So let me just delete that. Of course, we can immediately identify that as 2 and 3. So you see H2's concentration varies there. It goes from 2 to 4, and NO's remains constant at 1. And there again, the rate varies. So we can see how the rate varies by changing H2's concentration. And hence we can see how that is dependent on H2's concentration. So we're going to say compare two and three. So you go through the whole thing again, and now you say rate of, you can write everything out, but you can also just say rate 2 or whatever you want to say, however you want to write it. There is a symbol that you can use. You can define it as a symbol. Rate of experiment 3. So you can immediately write what? Maybe you can immediately write it as is going to be equal to, because we know the NO is the constant, K is constant, so it's going to be H2 experiment 2 divided by concentration of H2 experiment 3. Remember, I'm skipping some steps. So if you need to write the steps to the power n this time. Substitute in the values, go look in the table, go through all the logs. You should get eventually to a point where on the left-hand side you will get a half is equal to a half to the power n. And therefore, n is going to be equal to 1, because, to get a half, you have to raise a half to 1. So, therefore, n, and hence, the reaction is first order in terms of hydrogen. So, this means that if you were to double the concentration or the in terms of once again, if you were to, for example, double the concentration of hydrogen, the rate will only double. If you triple the concentration of hydrogen, the rate will only triple. Not with like NO. If you doubled the concentration of NO, the rate would have quadrupled. You see, so that is what the rate in terms of a reactant means. Not the same as the overall reaction rate. What is the overall reaction rate? So at the moment, as we have it, therefore, currently, you can maybe say currently, so in brackets, just write for yourself currently. Because things are going to change still, rate is equal to K concentration of NO squared multiplied by H2, right? We still need to determine K. So therefore, the overall reaction rate, so overall reaction, order is third, which is equal to M plus N, which is 2 plus 1. It's 3. So in terms of NO, it's second order. In terms of H2, it's first order. The overall reaction is third order, which means if essentially you have dependence on 3 concentration order terms. So you can write it as third order basically just means it is concentration, concentration, concentration. The rate depends on at least 3 concentration terms. In other words, increasing the concentration of the reactant is going to cause an order of 3, of a power 3 change. So, in other words, increasing all of the reactants concentration, important word, all of them, doubling all of the reactants concentration, not just one, doubling all of them is going to have an effect of 2 to the power 3, in other words, multiplying the rate by 8 times. Right, because the overall reaction rate is a third order. Okay, you see how those different words just shift the idea. But okay, anyway. So that's where we are currently. The question actually asks, using the data dependent the overall reaction order, so that's third order, and the value of the rate constant K. So how do we get the rate constant K? Well, we can just plug in any one of those values because we can now solve for K. Let's choose a nice color, like the light blue. To obtain K, we then solve for K. So K is equal to the rate divided by the concentration of NO squared H2. Right, and what you essentially have here is you can write rate of experiment 1 over concentration of NO. Why do I do that? Concentration of NO of experiment 1 squared multiplied by concentration of H2. The whole idea was to write the subscript, experiment 1, which should be roughly equal to the rate of experiment 2 divided by concentration. I'm just going to drop the whole experiment, so concentration 2 squared H2 experiment 2. You get the idea. And the same with 3. So for 3 over that one. So you can choose any set of the data to calculate this K. I'm going to choose experiment 1 just because it's the first set, so you can then plug it in. So then it's 1.3 molar per second divided by 5.00 times 10 to the negative 3 molar squared, 2.00 times 10 to the negative 3 molar equals 2. Should get 2.6. Units wise, below you get molar cubed, so it's going to cancel. It's third order, so third order rate constant is per molar squared per second, which you can also write explicitly as 2.6. So it's 2.6. You can just check the significant figures as given, which is liters squared per mole squared per second. Okay. And you can check the others. Do yourself a favor and calculate it with experiment 2's data set and experiment 3's data set and see if you roughly get the same answer. You might not get exactly the same answer, but roughly. So, and of course, in any test or exam setting, you will be given the opportunity, you may choose any set of data. Yeah. So that's how you determine the overall reaction order. You determine the rate law, and of course, if you were asked, you're not directly asked here, but if you were to write the rate equation, you would now say, therefore, the rate is equal to 2.6 m to the power minus 2 per second multiplied by NO squared H2. So that is our overall expression for the rate. So that is the A part. So now we've got an expression for the rate, which is useful for the B part because it says determine the rates of the reaction when the concentrations are as given. So basically what you do is you just plug them into that equation that you just derived yourself. So you say B, because that's the B question. It says, therefore, our rate, we just take that equation as written, and equal to 2.6 per molar squared per second. Concentration of NO is given as 4.73 multiplied by 10 to the power minus 1 molar squared multiplied by 1.84 times 10 to the negative 3 molar. And you should get rounded a value of 1.1 times 10 to the negative 1 molar per second. Should see that the values work out as such. Molar, you have 3 molar on the one side, or 3 molar multiplied by per molar squared per second. So you'll end up with a unit of molar per second. And that makes sense. It's a rate. There is so many molar per second being consumed. So, yeah, it's as easy as that. It's not a lot, though. It's interesting, but also the concentrations aren't that large. I mean, it's technically very small concentration, these that are given for the reactant, so you don't expect a very large rate to be associated with that. Okay, I hope this made a bit of sense. The idea of reaction order, the idea of rate constants, and remember this is the idea of initial rates. How to determine a reaction rate and the rate law and the rate constant from a method of initial rates. And once you have the rate law, then you can determine the rate of a reaction given any set of reactant concentrations. All right, thank you for watching.